Hi there, folks. Today we're looking at piecewise functions. And piecewise functions are literally functions that we graph in pieces, all right? And so the thing that becomes important here is our kind of understanding of functions themselves, but also of our understanding of domain and range. So the piecewise function has kind of two pieces. It has what we're graphing, and then it has the domain, which is where we're graphing it. All right, so piecewise functions are a group of functions graphed on specified intervals. All right, in other words, I'm going to take one function and just graph part of it here, and then I'm going to take the next function and graph part of it here. All right, so I'm graphing these things in pieces. So I'm going to have little pieces of a bunch of different functions, and together they're going to make up my piecewise function. All right, so for example, here's kind of what this looks like. And so when we look at this example, it says f of x, so the function equals, and then it splits it. The function equals these two functions graphed in these specific places. And you notice here, there's kind of two elements written here. I've got this guy, which is an actual function, the 2x minus 1. But then I also have this guy, which is kind of written in the fashion of domain, and that's what it is. It's saying I'm going to graph y equals 2x minus 1, but I'm going to give it a domain of x is less than or equal to 2. All right? And then I'm going to graph the function y equals 5 minus x, but I'm only going to graph it using this particular domain of x is greater than 2. All right, and so what happens here is I kind of break the graph into pieces. So here's what I'm going to start with. I'm going to graph each of these functions completely, then I'm going to erase to adjust the domain of each. All right, so if I looked at this first one, again, if I were to ignore this stuff, if I just had two functions as f of x equals this first thing, 2x minus 1, well, that's got a y-intercept of -1 and a slope of 2, up 2 over 1, up 2 over 1. So that's what this graph would look like if I was just graphing that first function. All right, it's a line that has a y-intercept of -2 and a y-intercept of -1 and a slope of 2. If I were to look at this guy, if I were to graph this thing separately, well, you might have to rewrite it and say, oh, that's a -x plus 5. Well, again, that's a y-intercept of 5 and a slope of -1. So the graph would look like this. Oh, that was terribly shaky. I could think I can do better than that. I believe in myself. Nailed it. Okay, so if I were to look at each of these, this is what they would look like if I graphed them separately. But each of these has a domain restriction. It's basically saying right here, for this first guy, I only want the domain of x is less than or equal to 2. In other words, I can't graph that function where I have an x value of 3. I can't graph that function where I have an x value of 5. Okay, and so if I kind of come over here and say, you know what? That means this function should stop right here at this x value of 2. So let me erase the rest of it. So if I only graphed part of that function that had that domain of x is less than or equal to 2, that's what I would have graphed for that first function. Likewise with the next one, if I only use domain values that were greater than 2, I wouldn't bother graphing all this stuff over here. See, if I look at the stuff over here, this is domain values that are less than 2. And I only want domain values that are greater than 2. So if I kind of regraph this thing, I would only graph the bottom half of this thing. All right, I will only graph that. And so as we look at this guy, this is a piecewise function. The thing that becomes a little bit tricky is right here. For that first line, I would do a closed dot at this point. And for the second line, I would do an open dot. Well, if you have a closed dot and open dot on top of each other, all we see is a closed dot. All right, so these kind of came together. They don't have to come together. They just happen to in this particular example. But as we look at this thing, I have two different pieces of this thing, all right, graphed in certain spots. So instead of graphing the entire line, I graph a line with a modified domain, all right? And when you look at this thing, it kind of looks like an absolute value function. That's just this particular example looks that way. It's not an absolute value function, but we can actually graph absolute value functions as piecewise functions if we use lines that are similar in terms of the slope and that kind of thing. Okay? Let's look at another one. If I look at something like this guy, again, same kind of thing, except this time maybe instead of graphing each of them completely and erasing, let's see if we can just graph the pieces we need. Okay, so if I looked at something like this, the first function I have is essentially g of x equals x minus 5. Well, that's a y-intercept of -5 and a slope of 1, but the domain is only where x is less than 1, okay? So as I go to plot this thing, a y-intercept of -5 is right here, and I just ask myself, do I actually plot this point? And the answer is yes, because I'm at an x value of 0, which is part of the domain. And then I would go up 1 over 1 and ask myself, do I actually plot this point? And the answer is no, because 1 is not part of this domain. Actually, I would use an open dot here because there's no equal to condition. And if I kept going, if I went up 1 over 1 again, now I'm trying to plot, see, I'm right here trying to plot this point, but I wouldn't plot that point because I'm not in the domain that's being specified. I'm at 2 right now, an x value 2, which isn't part of my domain. And so what happens is I have to go the other way. Down 1, back 1. See, -1's part of the domain. I can plot the next point because it's at -2, and that's part of the domain. I'm only plotting the values that are part of the domain that's listed. Okay? Likewise, with the next piece of this thing, I've got y equals a -2x plus 1, so I would start with a y-intercept of 1. But again, a y-intercept of 1 would be right here at this point. But do I actually graph that point? See, right now I'm at an x value of 0. Is that part of the domain that's listed here? Well, no, 0 is not part of that domain, so I don't actually graph that point. But now from that point, I would go down 2 over 1. So it would be this point right here. And I ask myself the question, do I graph that point? I'm at an x value of 1. Is that part of the domain? And the answer is yes. X is greater than or equal to 1. I'm part of the domain. So now down 2 over 1 again. Do I plot this point? I'm at an x value of 2. So the answer is yes, that's part of the domain. And so as I keep going, I plot all these points. But if I were to keep going the other way, up to back 1, well, I'm at -1 now. I don't plot those points because they're not part of the domain. Okay? And an easy way to check this thing is as I look at this, I should look at the domain of each and say, hey, look at that first line. It goes to -infinity, starts at this end, and it goes all the way up to 1. It has a domain of x is less than 1. If I look at the second line, it starts at 1 and goes up from there. It has a domain of x is greater than or equal to 1. Okay? So I'm graphing this line and then tweaking the domain a little bit. Okay? The other way that I tend to do this is I'll tend to look at the domain values first, and I'll set up a little barrier for myself. So like here, when I do this, I immediately say, okay, I want to cut this thing off at 1. So I usually just draw a little dotted line right here at 1 so that I know where my functions are stopping. Say I set the graph up in terms of domain first. I say, hey, over here is where it's less than 1, and over here is where it's greater than 1. Okay? And on the line is where it's equal to 1. And now I kind of establish the sections where I'm going to be graphing this thing. Okay? So if you want to, break the graph up ahead of time in terms of the domain, and then only graph the function that belongs in that domain. All right? For example, if I kind of do that with the next one. Right here, when I look at the domain, so if I ignore everything for a second and I just look at the domain on each of these things, I've got one that's less than -2. So let me draw a little dotted line at -2. So everything to the left of that line is where x would be less than -2. Okay? And then the next one I see greater than or equal to -2, but less than 1. Well, here, let me draw a dotted line at 1. And you see in between these two values, that would be the x values that are between, let me redraw it here, between -2 and +1. And then, of course, on this actual line is where x equals -2. On this actual line is where x equals 1. But then over here in this section is where x is greater than 1. See, I'm just breaking the graph down into those domain sections. I've got a section that's greater than 1. That's all this stuff over here. I've got a section that's between 1 and -2. That's this section in between. And I've got a section that's less than -2, which is all this stuff over here. See, the graph is broken down into 3 sections, and it's broken down into the 3 sections represented by these 3 domain restrictions, essentially. Okay? So now I just graph in each of those sections. So in the first section, the section off to the left, the less than -2, I'm going to graph the function y equals 2x. Well, to graph y equals 2x, that has a y-intercept of 0, but I don't actually plot this point because I'm not in the right section. And then normally I would go up 2 over 1. But I'm still not in the right section. See, as I try to track this thing, I was here, then I was here, then I'd be here. And as I start to look at these ordered pairs, think about when I'm in the right section. I'm only in the right section when I hit these values over here. Okay? So I can get rid of the rest of those. So I graph the line the same way I would normally graph the line, but I only graph the pieces that appear, and I just erased a little bit too much. I only graph the pieces that appear in the right section. And apparently I can't get it without, so I'm just going to leave that little red guy. But then on this line itself, I use an open dot because there's no equal to condition for the domain. In that middle section between -2 and 1, I want to graph the function y equals -4. Well, that's the equation of a horizontal line. So that's this guy right here. And again, if I were to continue past this section, I don't want to graph that over here. I don't want to continue that line over here because that's the wrong section. That's not the domain that's stated for that function. Okay? But now I need to decide what to do on each line. Over here, I have an equal to condition. Over here, there's no equal to condition. So I use an open dot and a closed dot respectively. Okay? And then the last one, y equals an x minus 4. So again, it's got a y-intercept of -4. That's down here. But again, I don't actually plot that point. I don't want to plot this point because I'm not in the right section. And then I would go up 1 over 1 to this point, and then up 1 over 1. But I only want to graph what's in the right section. I only want to graph that thing over here. And again, I can get rid of those little red guys that are all over the place. But now I have to decide what to do on the actual line here. There's an equal to condition, so use a closed dot. All right. And once again, some of these touched and some of them didn't. It still passes the vertical line test. But the point is I'm graphing the lines the same way I've always graphed them. The difference is that I don't graph the whole thing. Okay. I only graph it where it says I should graph it based on the domain that's written. Okay. Again, if I look at this guy, I'm going to break this thing down in terms of the domain first. Okay? And again, you don't have to do this. You could graph each of these completely and then erase pieces to adjust the domain. I like to do it this way. I like to say, okay, here's my domain value. So I want less than 2. Well, here's 2 right here. So everything to the left of that dotted line is where the graph has x values that are less than 2. Everything to the right of that line is where things are greater than 2. And then, of course, at the line is where it equals 2. Okay? So that first function, y equals 3x minus 1, it's got a y-intercept of -1 right here. And then it's got a slope of 3, up 3 over 1. Or down 3, back 1. And I just have to ask myself, am I in the right section? I only want to graph that line in the x is less than 2 section. That's where I am, so I'm graphing in the right place. But as this thing continues, if I go up 3 over 1 again, now I'm on the line. And the question is, does this function touch this line? The answer is no. I use an open dot because there's no equal to condition for my domain value right here. Okay? And of course, I could keep going up 3 over 1, but I don't plot the next point because now I'm in the wrong section. Okay? I limit my graph to the section that has those domain values. And then the next one, y equals 5. It's got a y-intercept of, it's just a horizontal line of 5. So it'd be a horizontal line up here. And again, if I drew that entire horizontal line, it would look like this. But I don't want the entire thing. I only want it where I have domain values that are greater than or equal to 2. So I only want to graph that horizontal line over here. And then on the line itself, I fill in the dot because there's an equal to condition. Okay? And once again, here they touched, here they connected, but that's not always the case. Okay? This is what piecewise functions look like. I'm graphing pieces of each of those functions. If I look at this one, this one's a little bit more on the ridiculous side. I just wanted you to see something like this. This is called a step function. You'll see why it's called that in a minute. But if you look at this, these are all constant functions. I've got y equals 1, then y equals 0, then y equals -2, okay? But I've got this thing broken down. Let's see, -4 is back here somewhere. -2, 0. So this one's broken down to a bunch of little sections. 2, and then 4. And as you look, like this section right here, this is the section where the domain values are between -4 and -2. And between -4 and -2, right here, I want to graph y equals 1. So let me graph the function y equals 1 in here. That's right here. It's a horizontal line. And then I have to decide, okay, over here it's a closed dot and over here it's an open dot because of where I have the equal to versus no equal to conditions. If I look at the next section, right here, this section of the graph is where I have domain values between -2 and 0. And between -2 and 0, here's that domain. I want to graph the function y equals 0. So I graph the function y equals 0. It's a horizontal line right here at 0. Again, closed dot on this side and open dot on this side based on where I have those equal to conditions. The next section of the graph right here, those are the domain values between 0 and 2. And between 0 and 2, right here, between 0 and 2, I want to graph y equals a -1. So I graph y equals -1, this horizontal line. Again, closed dot here, open dot here, based on where I have those equal to conditions. And then the last section I have right here, this is the section between 2 and 4. Well, here's that section listed. Domain values from 2 to 4, I want to graph y equals a -2. That's the horizontal line right here at -2. Again, closed dot, open dot. Okay? But again, I'm graphing a bunch of horizontal lines, but I'm only graphing a little piece of each of those lines. That's a piecewise function. All right? This is a special kind called a step function, and hopefully you can see that this looks like steps. Okay? There are certain things in reality that use step functions. A lot of times hourly pay works on a step function. They won't break it down by minute, all right? Maybe they'll break it down by 15-minute increments. So once you break into that new 15 minutes, you jump up to the next level of pay. Tax scales work the same way. They're step functions, okay? If I look at this guy, a little bit of a challenge thrown in here. Ready? Whew! Got some absolute values in there. Again, I'm going to break the graph down in terms of those domain sections first. So I've got it -3 right here. So everything to the left of that is where x is less than -3. And then from -3 to +2 is right here. Again, this section is between -3 and +2. All right. And then over here, this is where x is greater than 2. All right. And of course, on the line, this is where x equals -3, right on that line. And right here, this is where x equals 2, right on that line. And really, those only come into play when I'm deciding open dot or closed dot for these things. Okay. And so if I look at this first function, this guy right here, that's an absolute value function, which means I'm talking about vertex right now. So the vertex of that guy is -4, -2. Remember, it's the opposite of the guy that's inside there, and then the other guy just as it is. Or you can think about it in terms of transformations. I'm shifting left to right, up or down. So this one shifts to the left 4 units and down 2 units. So this one has a vertex of 4, 2. It opens up because the a value is a 1. And I kind of use that a value like the slope. So my slope is kind of like a 1, but I make sure the v opens up. Okay? And so again, I only want to plot that in the less than -3 section. So let's see if the vertex actually makes it there. -4, -2 is right here. I'm in the right section. So I plot that point. Okay. And then it opens up with a slope of 1 in each direction. Over here, up 1 over 1. And I have to decide open dot or closed dot here. There's a closed dot. But I don't keep going. The v stops right at that line. I only want to graph it in this section because that's the domain that's listed for this thing. And you see the equal to condition, that's why I used a closed dot on the line. Okay? Now I move on to the next one. Y equals a 1/2 x minus 1. That goes in the middle. Well, that's got a y-intercept of -1 and a slope of 1/2. So it's up 1 over 2. I'm on a line here at 2, and that one's going to be an open dot because there's no equal to condition, or down 1, back 2. Again, down 1, back 2. Now I'm in the wrong section. Right here is where it's kind of hit that guy, so it's an open dot. But again, I'm just graphing that line, but only in the middle section. And the reason I have those open dots is because there's no equal to conditions listed for my domain. And then the last one here, once again, this is a absolute value function, so let me write it off to the side again. The vertex is 5, 0 this time. Okay. This one's going to open down because the a value is a -2. And we're going to kind of use that like slope. The slope's going to be, in general, 2, but in the downward direction. Okay, so +2 and -2. So let's try to plot the vertex. Let's see, 5, 0 is right here. I'm in the right section, so I'm allowed to plot that vertex. And then it's down 2 over 1 in each direction, down 2 over 1 in each direction. I could keep going this way, but then over here I run into the line, open dot or close dot. Well, that one's going to be a closed dot. But then I stop. I don't keep going because beyond that line, I'm outside of the domain that's listed, okay? That function only gets graphed in the greater than 2 area, and I get a closed dot on the line because of the equal to condition. This is a piecewise function. I'm graphing 3 different functions, but I'm only graphing pieces of them based on the domain that's listed, okay? All right, so in these last couple examples, we're just going to plug some things into piecewise functions. And really, this comes down to knowing 2 things. One, it's remembering function notation. Remember, in function notation, whatever's in the parentheses, that's what we plug in for x, okay? But then 2, with piecewise functions, remember, everything's defined based on these kind of restricted domains. So when I go to plug these things in, I have to decide which piece of the piecewise function to plug that value into. And that's all based on the domain. See, each of the pieces inside a piecewise function uses specific domain values, uses specific x values. So I have to determine when I see the x value I need to plug in, which piece of the function I have to plug it into. So for example, if I look at something like this guy, I've got f of 2. All right, and so I have these 2 functions, f of x and g of x. They're both piecewise functions. But if I look at f of 2 is telling me to plug a 2 into the f function. So right away, I know I'm dealing with this first function, okay? But now using a 2 in that first function, I'm only going to plug this into one of the pieces of this piecewise function. So I have to look at the domain. Like right here, this first piece uses x values that are less than 3. The second piece uses x values that are greater than or equal to 3. And so if I have an x value of 2, well, that's an x value that's less than 3, which means I only want to use the first part of this function. See that guy right there, the value of 2? That's less than 3, which means I only use the first piece of this function. So when I plug f of 2 in, when I do f of 2, I only plug it into the 2x minus 3. I don't plug it into the second piece of this piecewise function because the second piece doesn't use x values of 2, okay? And so again, the piecewise functions are defined by these domains. So if I have a domain value of 2, I need to find the piece of the piecewise function that uses domain values of 2. Okay? And so I plug it in. F of 2 equals a 1. And that's it. I'm done. Okay? If I look at the next one, it says g of 3. So now I know I'm plugging into the g function this time. So I'm plugging into this second function. I'm plugging into the g function. But I only want to plug it into the right piece of this function. And so I have to look at the domain. And as I start looking at these domain values, so like this one uses x values that are less than -2. This one uses x values between -2 and +1. And this uses x values that are greater than or equal to 1. And so if I have g of 3, that falls into that third category. 3 is greater than or equal to 1, which means I only use this piece of the function. So I'm going to plug it into the x plus 3. Okay? So it's a matter of determining, all right, based on this domain value, which piece of the function do I want to use? This one with a domain value of 3, I want to use that third piece. So g of 3 equals a 6. Okay? If I look at the next one, once again, this time I have g of -1, so I've got to scroll back up here. So -1, I'm looking for the domain value of -1. So I have to look at this and say, okay, which of these 3 pieces uses the domain of -1? And the answer is it's this middle one right here. This guy uses it because right here, -1 is between -2 and +1. So only that middle piece of the function uses this, so I have to plug the -1 in there. And students sometimes get confused by this. You know, g of x equals 6 means no matter what I plug in for x, it's going to equal 6. So if I plug a -1 in for x, well then guess what? Y is going to equal a 6. That's what a constant function like that means in terms of plugging things in. Okay? And then the last one here, f of 3. So I know I'm going to go to the f function. So I look over to the f function. I have a domain value of 3 that I want to use this time. So I have to just decide, do I plug this into the first piece or the second piece? All right, which of these pieces uses domain value of 3? Well, right here. There's the equal to condition for 3. So this is the function I want to plug it into. That's the piece of the function I want to use, the 3x minus 2. So I'm going to plug that in here. 3x minus 2, and I just simplify. Okay? So again, the idea behind piecewise functions is I've got multiple functions, but I'm only graphing pieces of them. I determine which pieces based on the domains that are given. And so as that translates into plugging these things in, well, function notation's telling me which function to plug it into, but then the value that I'm using, I have to determine where that domain is, and that tells me which piece to plug it into. Okay?